Hi, good morning everyone. I am K. Narsimurthy. I work in a government first grade women's college Tumkur. I am going to present my 21st video for second semester BSc students of Tumkur University. The subject which I am discussing is physics. I have started the second unit and this is my sixth video in the second unit. 5 videos are over in the second unit. I mean to say a kind of a small chapter is done in the second unit. Second unit is all about magnetostatics. So I have explained a very famous law which is Biot-Savart's law. And using Biot-Savart's law, I applied the Biot-Savart's law for different situations and different kind of objects, which is a finite length conductor carrying current, and for a circular coil and for a solenoid. I found the magnetic field using this Biot-Savart's law. After that I discussed Ampere circuital law and I found the magnetic field of a solenoid using Ampere circuital law as well. After that I discussed many problems which is pertaining to these different cases, means these different applications of Biot-Savart's law and Ampere circuital law as well. It's a kind of a small chapter is done in the second unit. Now I'm going to do the 21st video, I mean to say the first video in this chapter, which is magnetic field and the force. Right. Now we are looking for the motion of a charged particle in the magnetic field. Now you know what is magnetic field is. In a simple words I can say that the magnetic field is the area around the magnet. Or you can say the area around the current carrying conductor. Okay. So current carrying conductor will produce us a magnetic field around it, and this is known as magnetic effect of electric current, which I told you in my previous video. Now what I am looking here is I am looking for the force which is experienced by a moving charge when it is placed in a magnetic field. Okay. Now we have a magnetic field in this direction which I shown you in the diagram, and we have a velocity vector, and the angle between the velocity vector and the magnetic field is theta, and a force is experienced by the moving charge when placed in a magnetic field. Okay, so this is known as mechanical effect of electric current. So what do you mean by mechanical effect of electric current? A moving charge will experience a force when it is placed in a magnetic field. So this phenomenon of a moving charge experiencing the force in a magnetic field is known as mechanical effect of electric current. And now I am going to find the magnitude of force which is experienced by moving charge in a magnetic field. Now I can say that the force experienced by the charge is proportional to the magnitude of charges. If more charge, it experiences a more force. Less charge, experience a less force. And is directly proportional to the component of velocity which is perpendicular to the direction of magnetic field. Look at the velocity and look at the component of velocity. We have a velocity in this direction, okay, which makes an angle theta with a magnetic field. If I take a component of magnetic field in the perpendicular direction, it will be V sin theta. Along the magnetic field, the velocity component is V cos theta. I don't want that. I want component of velocity in a perpendicular direction, that means to say along x-axis. Component of velocity along x-axis is V sin theta, and the force will be proportional to V sin theta here. Okay, so component of velocity along the perpendicular direction of magnetic field. And also the force is directly proportional to strength of the magnetic field. If more magnetic field you apply, the charge will experience a more force. So these are the three things. One is charge and the velocity and the magnetic field. Okay, if I'll try to write an equation from these things. So it is the F which is equal to Bqv sine theta. The force experienced by the charge moving in a magnetic field is given by F equals Bqv sine theta, or F equals Q into V cross B. That's a vector form of writing the force. Q into V cross B, or Bqv sine theta. Okay, so the direction of magnetic field will always be perpendicular to the plane containing both V and B. Okay, direction of force will always be perpendicular to the plane containing the velocity vector and the magnetic field. I will clearly explain you what will be the direction of magnetic force using the Fleming's left hand rule. Okay, I'll explain you that later in the by using the Fleming's left hand rule. Right, now we will discuss the cases in this. If Q equals to 0, what will be the force? If the charge is 0, if there is no charge at all, if there is no charge in the magnetic field, if it is a neutral particle, it does not experience any magnetic force. Any neutral particle will not at all experience any magnetic force. So magnetic force to experience, you need to have a charged particle moving. Case 2. If suppose velocity is 0, if the particle is not at all moving, if the charged particle is at rest in a magnetic field, so again in that case also there won't be any magnetic force. In case 2 also, you cannot expect any magnetic force to act on the charged particle which is at rest in a magnetic field. Case 3, suppose if theta is 0, what is theta here? Theta is the angle made by the velocity vector with the magnetic field. Velocity, magnetic field. So angle between the velocity vector and the magnetic field. If that is 0, I mean to say the charged particles are moving along the direction of magnetic field. Charged particle moving along the direction, or charged particles are moving parallel to the direction of magnetic field. So it does not experience any magnetic force. It is sine theta. It is Bqv sine theta. Theta is 0 means the sine 0 is 0. So F is 0. So force is 0. If a charged particle moving parallel to the magnetic field, they never experience any magnetic force. In the fourth case, if I look for the angle 90 degree, suppose angle between magnetic field and the velocity, the charged particles are moving perpendicular to the direction of magnetic field. In such a case, the charged particle will experience a maximum magnetic force. It experiences a maximum force, and the maximum force is F is equal to Bqv. This is the maximum force a charged particle can experience if it moves perpendicular to the direction of magnetic field. Right. So these are the some of the different cases which I discussed, and I looked for the force experienced by a charged particle in these cases. Now the point to be noted here is a charged particle traces a circular path in a magnetic field when it is moving perpendicular to the direction of magnetic field. Okay. So if a charged particle is moving perpendicular to the direction of magnetic field, definitely it will trace a circular path, not a straight line. Okay. So that is the one thing to be noted. The second point is a charged particle traces a straight path. It will go straight when they are moving parallel to the direction of magnetic field. It goes straight. Why? Because it will not experience any force at all. A charged particle which is moving parallel to the direction of magnetic field will never experience any force. Therefore, it tends to move in the same direction. So it moves in a straight line itself. One more third point which has to be noted here is a charged particle traces a elliptical path, helical path in a magnetic field when it moves with an angle greater than 0 and less than 90 degree to the direction of magnetic field. Okay, So this is the direction of magnetic field. If a charged particle is moving with some angle which is greater than 0 and less than 90 degree, say it's a 30 degree, it will experience helical path. Say it's a 60 degree, it will experience helical path. Say any angle between 0 to 90 degree, the charged particle will move in a helical path. Okay, because those charged particles will definitely experience a magnetic force, and therefore they started tracing an helical path. Okay, so these are the three different points to be noted when I discussing the force experienced by a charged particle in a magnetic field. Right, I told you what could be the direction of the force which is experienced by the charged particle. It is very clearly explained by the Fleming's left hand rule. So first you stretch the first three fingers of your left hand, which are mutually perpendicular to each other. Say this is my left hand, I am stretching the first three fingers of left hand and they are mutually perpendicular to each other. Okay, now this forefinger will direct the direction of magnetic field. Okay, the forefinger points in the direction of magnetic field and the middle finger points the direction of current. So the thumb will gives us the direction of magnetic force. Okay, I'll repeat this. If you stretch the first three fingers of the left hand like that, when they are mutually perpendicular to each other, then if this forefinger points the direction of magnetic field and the middle finger points the direction of current, so thumb will gives you the direction of magnetic field. Okay, so this is the direction of magnetic force. This is the direction of force. Okay, this is field, magnetic field, this is current, and this is the direction of the force experienced by the charged particle when it is placed in a magnetic field. Okay, it is a current means it's a velocity. It's a velocity. The current means it's a velocity direction. This is the direction of velocity and this is the direction of magnetic field. This will gives you the direction of the force experienced by the charged particle when it is moving in a magnetic field. Right. So after knowing the magnitude of force, which is Bqv sin theta, and the direction of force which is given by the Fleming's left hand rule, now with the same equation I am trying to define what is magnetic induction is, what is magnetic field is. Okay, right. So take that equation which is clearly the force Bqv sin theta. In that equation, if charge is 1 coulomb and the velocity of the charge which is moving is 1 meter per second, and the velocity will make an angle theta which is 90 degree with the magnetic field, then I can say that force is equal to B, or B is equal to force. I can define B now as the magnetic induction at any point in a magnetic field is defined as the force. Magnetic induction is the force experienced by unit charge, Q is 1 coulomb, experienced by unit positive charge moving with unit velocity, V is equal to 1 meter per second, in a direction perpendicular to the magnetic field, because theta is 90 degree. So this is how I can define the magnetic induction with this formula. I'll repeat this. So magnetic induction is the force experienced by unit positive charge moving with unit velocity perpendicular to the direction of magnetic field. So the SI unit of magnetic field is Tesla, or it is Weber per meter square. You can say it is Tesla or Weber per meter square. So both are SI unit. You can use any unit for magnetic induction or magnetic field. I also define what is 1 Tesla is. So 1 Tesla, it's that magnetic induction at a point if 1 coulomb of charge moving perpendicular to the direction of magnetic field with a velocity of 1 meter square will experience a force of 1 Newton. Okay. So that is how I can define 1 Tesla is. How much is 1 Tesla? If 1 coulomb charge moving perpendicular to field with 1 meter square, 1 meter per second velocity, if that charge experiences 1 Newton, then the magnetic field there will be 1 Tesla. Okay. So that is how I can define the Tesla. Now there is something different, which is Lorentz force. Lorentz force means if a charge Q moves with a velocity V in a region where it contains both electric and magnetic field. The charge is moving in an area which contains both electric and magnetic field. So I am looking for the resultant force experienced by that charge which is moving in both electric and magnetic field. So first I'll take the contribution of electric field. The force due to electric field is Q dot E, Q into E. And force due to magnetic field is Bqv sin theta or Q into V cross B. So the charge will experience force due to electric field and as well as magnetic field. It experiences both the force. So one is Q into E, another one is Q into V cross B. It experiences both the force because it is moving in a region of both electric and magnetic field. So therefore I am adding these two. So therefore it is QE plus Q into V cross B. I can take out Q as a common factor. So it is force is equal to Q into E plus V cross B. This is called the Lorentz force. Lorentz force means it is the force experienced by the charge in a region of both electric and magnetic field. The resultant force is the Lorentz force. Right. Now I am going to find the magnetic force due to current carrying conductor. Okay. So current carrying conductor will also experience a force because current in the conductor means to say it's a motion of free charges in the conductor in one particular direction. Therefore, conductor carrying current, when it is placed in a magnetic field, every charged particle, every electron will experience a force. Thus the conductor also experience a force, which is resultant force of all the force due to all the electrons, all the charged particles. So now what I'll do is I'll find out the force due to each charge and I'll sum it up. I'll get the force due to all the charges, which means say force due to the current carrying conductor. Right, let me take a conductor of length L and area of cross section is capital letter A, which carries a current I and is placed in a uniform magnetic field B as shown in the figure. Okay, so look at the figure. Magnetic field is perpendicular to the conductor and is acting away from the observer. It's away from the observer. Still I need to consider some more data here. Let N be the number of electrons per unit volume, electron density. N is the electron density, number of electrons per unit volume, and Q is the charge on each electron. We know what is the charge on each electron, which is 1.6 into 10 to the power of minus 19 coulomb. I am calling it as Q. Q is the charge on the each electron and VB its velocity. I have defined all the thing. I is the current, L is the length of conductor, A is area of cross section and is placed in a magnetic field B, and N is number of electrons per unit volume, Q is the charge on the electron and V is the velocity. All the things I have discussed, all the things I have declared. Okay, now we'll see what is the magnetic force on each electron. You know, it is a very well known equation, F is equal to Bqv, not sin theta, because theta is 90 degree here. I told you the magnetic field is perpendicular to the conductor. therefore it is only Bqv. Now it is the magnetic force due to each electron. I have many electrons in this conductor. I have number of electrons which are moving in this conductor. I need to find out what will be the total number of electrons. I know electron density is N is number of electrons per unit volume. What is the volume of the conductor? The volume of the conductor is length into area of cross section. So it is NLA will gives you the total number of electrons in the conductor. Okay. So for unit volume, number of electrons is L. So N, number of electrons is N. For volume V, for volume L into A, the number of electrons will be NLA. NLA is the number of electrons in the conductor of volume V, which is equal to L into A. Next, now let me look for the force on the conductor of length L. The force is equal to total number of free electrons into the force experienced by each electron. This is correct. Okay. So force on each electron multiplied by number of electrons. We know how many number of electrons are there in the conductor. I just told you it is N into L into A. N into L into A is the number of electrons multiplied by force on each electron, which is Bqv. I'll get a very lengthy equation which is BnVAQ. BnVAQ into L. I am writing NVAQ in a bracket, but there is something in that. I am going to write some quantity for that. NVAQ. Let's see what I am going to write. Right. Now I look at the number of electrons which crosses any section of the conductor per second. I am looking for per second. So there comes the velocity. So it is NVA, number of electrons in that cross section area A. It is N into A. If I take per second, I need to write the velocity. Okay. So V is L by T. T is 1 second, means I am writing velocity as length. Okay. Instead of length, I am writing velocity. Okay. So NVA is the number of electrons crashing the area of the conductor per second. So if I multiply that with the charge, I'll get the current. Number of electrons and charge on each electron is Q. I will get the total charge. And total charge, rate of this total charge is current. Rate of flow of charge is current. So there I am taking 1 second. So therefore it is NVAQ will gives you the total current. Total current is number of free charges into charge on each electrons. Right. I got current as NVAQ. That is what I told you. NVAQ. So these, go back and see the equation 1. Within the bracket I have written NVAQ because this NVAQ is the current. Okay. So instead of NVAQ I can substitute I in the equation 1. Substituting this in the equation 1, I got force as BIL. Instead of NVAQ I have substituted I. So it is BIL. So in general, if this conductor is making an angle theta with the direction of magnetic field, if it is 90 degree, fine. If it makes an angle theta with the magnetic field, I have to write this F as BIL sin theta. So it is BIL sin. If it is making an angle 90, it is fine, it is BIL. Now, in sometimes the magnetic field may not be perpendicular to the length of the conductor, that is making an angle theta. In that case, I have to use the formula BIL sin theta. So this is the force experienced by a current carrying conductor in a magnetic field. F is equal to BIL sin theta. Let's write a vector form of this. You know how to write a vector form of this. It's F is equal to I into L cross B. If there comes sin theta, you write cross product. If there comes cos theta, you write a dot product. That's a simple thing of writing a vector form. Now I'm getting sin theta, so it is good to write a cross product. So F equals I into L cross B. So let us discuss some case here also. So if theta is 0, what is the meaning of saying theta is 0 or 180 degree? Means it is parallel. What is parallel? The conductor carrying current is parallel to the direction of magnetic field. Then look at the force experience. There won't be any force. F is 0 because sin 0 is 0. Suppose the conductor is parallel to the magnetic field, it will never experience any magnetic force because sin 0 is 0. So F is 0. That is the first case. Suppose if it makes an angle of 90 degree, suppose the conductor will be perpendicular to the direction of magnetic field. A conductor carrying current placed perpendicular to the direction of magnetic field, definitely it experiences a maximum force. F is equal to BIL. Okay, these are the two cases. When the conductor is parallel to the magnetic field, it never experiences a force. If the conductor is perpendicular to the magnetic field, it experiences a maximum force of BIL. So these are the two cases I can discuss while saying the force experienced by current carrying conductor when it is placed in a magnetic field. Okay, right, these are some of the books which I referred. This is a very elementary topic. You can refer any books for that matter. These are some of the standard books. You please go through it. You can understand the things better. Thank you.